I know what you're all thinking. When are we going to go back to the Khan Academies or the trophies or the FETs or the things they can do at the computer and stop writing problems out? They're coming. But it's tough to find good, actual, reasonable, relevant problems about pulleys online, so we're going to have to just kind of pull through this and get through it. Today, we're talking about pulley systems and elevators. Now, on the right is actually the motor for an elevator, and we're going to really get into how elevators work. In fact, I'm actually going to attach an additional YouTube link in your assignment that's going to be about a 3-minute video about how elevators work. It's really fascinating. I highly recommend you watch it. It might even help you do the assignment. And a pulley system would be what you see here on the left. When you have many pulleys working together on the same object, it actually creates what's called a mechanical advantage and lowers the force necessary to lift the object. So because there are so many pulleys here, it actually lowers the force necessary to move it. The same way in a lever, the further away from the fulcrum you went, you would need less of force to balance something. So we're going to kind of see how all this plays out today. So I don't know if you guys know how elevators work, but elevators are essentially a sophisticated Atwood machine. If you remember, the Atwood machine had 2 weights on either side of a pulley. A lot of people think that there's just some cords that pull the elevator up and down, but it's not quite that simple. Elevators have what's called a counterweight. You can't see it, it's in the back of the shaft, or it's designed so that you would never actually see it in the operation of an elevator, but it moves as in the other weight of the Atwood machine. Pizzuto, what do you mean by that? Essentially, this is a simplified version of what an elevator looks like. You have the elevator on one side and you have the counterweight on the other. But wait, Pizzuto, hold on. Let's think about it. How does that make sense? Well, the motor right here at the top, doesn't have to lift the whole weight of the elevator every time it moves, because the counterweight is pulling the elevator too. So the motor with the counterweight, can lift the elevator up way easier than if just the motor all by itself. If it was just the motor all by itself, it would take way more energy. But the use of the counterweight actually helps move the elevator up and down, kind of like a sophisticated Atwood's machine. The difference is, though, is that the elevator doesn't just fall down when you let go of it. The motor holds things in place, and there are other safety mechanisms that you can see about how elevators actually work. So let's just think about it. So an elevator is nothing more than half of an Atwood's machine. So here's an elevator. We don't even care about the rest of it. Don't care about all that. Technically, I know in the elevator shafts that exist in the world today, there are safety features, but for all intents and purposes, an elevator is a freely hanging object. It gets pulled up and down. It's got to be freely hanging so it can move. If it was attached to all these things, how would it move up and down the floor so easily? So if an elevator is designed to hold a maximum of 1,500 kilograms, the car and the people total, so the weight of the car and the weight of the people in it, all right? All of this together has a mass of 1,500. And we know that this elevator can have a maximum acceleration of 3 meters per second squared. So essentially what we want to figure out is, what is the tension that this elevator can support? Because I don't know if you've noticed, but sometimes elevators have maximum weights. It's like, do not put more than 300 pounds in this elevator. How do they get that? They get it from equations like this. What do you mean by that? Well, let's see. We know the tension equation from the other day is mg minus ma for a freely hanging object, and we could treat an elevator to be a freely hanging object. So let's figure out what the tension of the cord is for the 1,500 kilogram car that is accelerating .3. So I'm going to do 1500 times negative 9.8, and then I'm going to do minus 1500 times 0.3, and I'm going to get the tension of that rope is negative 15,151. Excuse me, 150. So what we can assume is that because this was the maximum acceleration that it could withstand, that this is really the maximum tension that that cable can withstand before that cable gives out, and then the safety features of the elevator will have to kick in. So, however, the question is, what would the same elevator's maximum acceleration be if there was 1,800 kilograms held on the cable? So we now know the tension of the cable. We now know that. So now what we want to do is we want to use the same equation again. F of t equals mg minus ma. So what we're going to do is we're going to take the negative 15150, keep it negative, it'll just keep everything a little bit easier. But instead of using 1500, we're now going to use the 1800. 1800 negative 9.8 minus 1800A, because if it's holding more mass, it can't accelerate as much. So I want to find out what that new acceleration would be to understand how fast the elevator can actually go while carrying more weight than it should. So I'm going to type all this into my calculator. I'm going to multiply these two, and then I'm going to add them to both sides. And then what I'm going to do is I'm going to have 2490 equals negative 1800A. Then I obviously just simply divide, and I get negative 1.38 is the maximum acceleration that that elevator can experience while carrying 1,800 kilograms. So obviously with more weight, you can't move as fast. And eventually you may not be able to move at all. So when you deal with elevators, you're still using the tension equation. But just pay attention to just pay attention to just the circumstances. All it is using that equation to figure out there's going to be some constants, like the cable can only support so much. You know, the mass tends not to change. And you can kind of figure out questions like this. So you might have a problem-solving question like this in your homework tonight. So this is the harder part, because this is a little bit more conceptual. Here is an example of mechanical advantage. And I haven't really defined the term mechanical advantage, but essentially mechanical advantage is simply using a machine to do a task with less force. Using levers allows you to open doors with less force if you know how to use lever correctly. Using a wheel allows you to move with less force if you know how to use it correctly. And using a pulley will allow you to move an object with less force if you know how to use it correctly. So let's examine this situation, because this is a really crazy picture here. If the guy is pulling down on this rope, okay, let's think about the direction that that force is going. So if it's getting pulled down, it's getting pulled down, again, it's getting pulled down. Think about how the force is getting pulled. So if it's getting pulled down here, it's getting pulled up here. And it's kind of difficult to see, but the rope is going like this, all the way down, 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 around this, up, around this and back. So if you think about it, what is happening here is you have found a way to divide the weight of this object of 150 pounds. And that weight is now distributed among the 3 different parts of the string. Remember, the tension in a rope needs to be the same. So these numbers cannot be different. They all have to be the same. You have 3 different points in which the string, the rope, the wire, the cable is pulling it up. So because it's being pulled up at 3 different points, you can take its mass, divide it by 1, 2, 3. So that means there's only 50 pounds of force in this rope, meaning you can pull with only 50 pounds of force to lift a 150-pound object because of these pulleys. It divides the force required to move it by every string that's attached. You're going to see a little bit more. So here is another example of a pulley system. So the red is the string. Here's the weight is right here. And what it's saying is, why is it saying 1/4 on the string? Well, let's think about it. From the weight's perspective, how many upward forces are acting on the weight? Let's not worry about the halves. We're not going to do the halves. We don't care about those. Let's just look at the red fourths. 1, 2, 3, 4. From the perspective of the weight, it's getting pulled up at 4 different points. So that means you can reduce the force necessary to lift it by to a fourth. Divide it by 4, because there's 4 ropes holding it up. Each pulley attached to the weight reduces the force required to lift it by 2, because each pulley brings up 1, 2 ropes to hold it up. It's got to be attached to something up here, but then as it comes down, another pulley divides it by another 2. So let's see what this means in practical ways. More pulleys means less force. So here are some real life pulleys. They may not be as crazily separated as we had just seen with them looping around, but you might see multiple loops in the same object. Multiple loops in the same object, and what it's doing is it's creating some mechanical advantage by looping it around multiple times. It is helping to lower the force required to lift it. So a crane is moving a 925 kilogram piano with a pulley system looped 5 times. If the piano is accelerating -2 meters per second squared, what is the tension in the rope? Okay, so let's see if we can kind of picture this. So here's the crane. I don't know how to draw a crane. Here's the crane. There it is. And it is lifting, let's just say, so the rope is here. And because I say it's looped 5 times, it's going to go 1, 2, 3, 4, 5. Oh, geez, I should have made the crane longer. Attach. And then this is the piano. And let's just assume that it has 5 pulleys attached. And all these are pulleys. Sorry, my mouse is struggling right now. Chugging right now. Okay. Doop, 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 doop. And then, of course, for anything to work, you need the pulleys up here too. The picture is really not that important. You don't have to draw pictures for these. But I'm just allowing you to, if you can understand what it's conceptually saying, is that it's got, when I say looped 5 times, what I'm saying is you're going to have 1, 2, 3, 4, 5 loops on the object. So this is what we need to do. If we're asking about tension, we're of course going to use the tension equation. So F of t equals mg minus ma. Okay, so the force of tension, all right, this isn't so bad. It's a 925 kilogram. Gravity is, of course, negative 9.8 minus the mass is 925, and the acceleration is negative 0.2. Okay, 925, negative 9.8 minus 925 times negative 0.2. Yes, 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 yes. That's right. So I'm getting the F of tension is negative 8.880. Awesome. That is the tension that's in the rope, total. But I said that it gets divided by 2 for every pulley. But with 5 pulleys, that force is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are now 10 places where that weight is distributed. So the tension gets divided by 10 because 5, it's looped 5 times. Each loop creates 2 sides of the string is 10. So that the actual tension in this rope is only negative 888 newtons. It lowers it by a factor of 10. That is how you deal with a pulley system. You solve for the tension normally, just like we had been doing all along, and then you have to figure out by the factor you have to divide by. It's actually pretty easy once you get the hang of it. But I drew this picture to kind of give you a conceptual understanding of why and where these numbers come from. The 10 comes from the fact that there are now 10 different ropes or parts of the rope holding up the piano. So that's it for pulleys. We're going to start something new next week. Try to get back to a little bit more sense of normalcy. But you will have an assignment, a worksheet to do some problems out on your own about this. Please check out the YouTube elevator video that I'm also attaching to this assignment. It's pretty cool, and it will actually explain elevators way more thoroughly than I did, and explain the safety features about them as well, which I didn't even touch. So please look into that. And again, I have office hours every day. If you have any questions, please do not hesitate to come by, and I will see you guys on the next one. Be well, take care, do good.